Okay, yes. Hi. Yeah, thanks for the invite. It's actually always nice to see what's happening on this side. This talk, I kind of renamed it. I called it Integrated Packaging Strategies, but basically with the aim of addressing the new challenges that we're having in shipping and cooling, and the fact that things are clamping down a lot in recent years, I guess, the recent 2 years. It doesn't work. Okay, yeah, so I estimated, this is an old stat I had, but yeah, that we're probably shipping about 45,000 containers a year for apple, pear, stone fruit, etc. And that this sort of trend will just increase because people want fruit all year round and they want all types of varieties on that table there. And then, of course, yeah, the big problem, and I assume it's the same for you guys, is that shipping costs have just spiraled out of control recently, particularly after COVID. Shipping lines are sort of reporting their biggest sales and biggest turnovers yet, and the price seems to be coming on us. And the trend is that this will probably not change. They have us now in a good position. The other side of it is that there's also a trend for low carbon, greener sort of setups. So there's a high pressure for a big shift in how we're approaching our containering shipping sort of processes. So I just listed some sort of stuff here. I showed for the container itself, when you're packing poem or stone fruit, particularly stone, you're wasting 10% of the floor area. And that's generally been considered okay up till now. And if you look at the fruit occupancy, so how much fruit is actually in that volume, it's only about 64 or 67%. So if we had a perfect carton, so if our carton was designed exactly for the container, of course the container and pallet system was designed originally for conventional shipping, then you would be able to save about 4,500 containers, or equivalently $30 million. So it's a big loss, but we kind of just don't look at it because, yeah, it's always been done like that. And then, of course, there's no standardization for packaging systems. It's just done, everybody does the same thing. So if you go in that picture over there, there's some South African citrus and then there's some Spanish citrus, and they're identical cartons. And below there's also melons and all sorts of strange fruit in this Rotterdam cold store, and everybody's kind of doing the same thing. My point here is just that we probably are furthest away from our markets compared to everybody else, so the onus is actually on us to do something. We would get the benefit. There's no real reason for somebody else to optimize this problem. And then I just said here that everybody's kind of reevaluating our usage of oil, plastic usage, even how we communicate with each other. This seems like a good time to reevaluate how we're doing this supply chain system. Okay, and I just wanted to also talk to you guys about sort of designing and optimizing. The packaging system or packaging optimization is actually what we call an NP hard problem, and that just means that as you change variables in the problem, the other solutions have to also be reevaluated over and over again. So as you add more dimensions, it basically just goes into an infinite number of tests that you would have to perform to find like an optimal space. So I've illustrated this with this little graph at the bottom. Let me shift to a laser. There it is. At the X plane, I'm just showing the design space, and you would obviously find new designs with, investment in research, time, energy, etc. And then the Y-axis is your, how optimal the carton is. And I would say at the moment we're sitting here, sort of a local optimum position. So when we change something, it kind of feels like it gets worse. But probably, and very likely, just from this research, there is a global maximum. There is a better solution for the space that we have, or the design we have. It's just a trick of finding it. I just showed here that this is actually a one-dimensional plane. Here's an example of a two-dimensional plane. There's no way to visualize now a third or fourth sort of dimension, but probably we're running in more than 100 dimensions. So there's the footprint, the pallet, its strength, etc. All these things have to add up, and all of them have to be optimized in context of each other. So it's a very complicated space. But the process of improving a package can be simplified. You can just need to sort of assume certain things. So the first one is that the container is immutable. The container, or at least the refrigerated container, is being used by many other organizations around the world, and they probably have a priority over us. So we're not able to change that container and how it's used. So we're locked in with the space in that container. The other factor is the pallet footprint, so the actual pallet base. We know that all these facilities have been set up effectively for a 1.2 by 1 meter pallet. And they do handle smaller pallets and sort of a little bit bigger. But in general, if we have a pallet that size or a little bit smaller, they will probably be able to accommodate us. So those are two nice boundary conditions to work with. And then within those boundary conditions, if you just try and optimize now for packing density and cooling performance, then this is where sort of I carried on. So using those two criteria, or four criteria actually, we developed two cartons. Sort of we tried to go in very different routes. The first one is a TESS, standing for Tessellate. So what's special about this carton is every face of the carton is actually unique. So the vent holes in slightly different positions. And when you stack it on a pallet, all the vent holes align very nicely and you get really good airflow alignment. And then the other one is the hex carton, so for hexagon. And the idea here was to have, like a honeycomb kind of carton design. But it's not really possible to do that. So what we did was sort of a half a hexagon shape. And then if you put them together, it forms a hexagon kind of, it forms a hexagon kind of cone shape. Especially when you stack it on a pallet base itself. And there's probably some advantages here with the hex, although it's a little bit more tricky. It seems like when the sharp angles of the carton are folded, you get quite a strong carton. And it also lines up well with hexagonal close packing, so where the fruit are stacked inside a carton. So you get less wastage of spaces in the corner. So here's just showing a picture of a container itself, and then I'm going to show you some pictures of them from the top using these different packaging systems. So here they are. The first three containers are sort of your standard Mark IV 1.2 by 1 meter pallet. The top one is with 20 pallets. The next two are with 21 pallets. I believe there's now a 22 loading strategy, but some funny playing around with the pallets themselves. But here is with the TESS and with the hex at the bottom. So using the TESS, you can use your floor area basically 99%, so your whole floor area is covered. And then with the hexagonal close packing or the hex carton, it's 97%. So just maximize the table here. So yeah, I think what's probably most interesting here is that with the fruit sort of volume inside the container, because that's what we want to pack, using a 21 pallet loadout with a standard pallet, you get about 19.8 tons of fruit in it. With the TESS, you get 19.8 as well, so very similar. With the hex, you get about 22.4 tons. But yeah, just going from that's our density analysis. Looking at the cooling, we broke this problem up into two sections. First, we looked at sort of horizontal cooling and then vertical cooling, just to get the properties of heat transfer and airflow resistance. So we ran some simulations and we kind of just showed, we just took these properties. And then we took a porous media approach with these properties that we derived from the previous simulations, and we put them into a full 3D simulation of a container to see how they perform in this environment. So yeah, basically here, there's the three standard cartons, or standard packaging, Mark IV, and it's really the same shape that we kind of all know. The left is where the refrigeration unit is, and the right is the door. This is viewed from the side. So basically, yeah, very high airflow rates at the refrigeration unit, and then as that airflow bypasses through gaps and corners, it just escapes back to the refrigeration unit, and then the result is very low airflow rates at the door region, and therefore very low cooling rates. So it's very hard to manage your cooling, especially for something like stone fruit where your respiration rates can run out of control. So this is not an ideal environment for those scenarios. With the TESS and hex carton, because we're covering most of the floor, and the airflow properties are actually very good because of the alignment, you'll see that there's a very even or uniform airflow distribution to all the cartons in the container. And that would mean that you have, very good cooling uniformity, and it would be superior in its ability to control the quality degradation in using these packaging. Okay, yeah, this is just a diagram showing some of the airflow. I think they will share the slides with you so you can take a closer look. Okay, so to conclude, the packaging designs we have now, just from the research we're showing here, are not optimal. So there's definitely space to improve. It's difficult to know exactly what that improvement would lead to, though, but it's definitely there. we can definitely also expect that shipping will become a bigger problem in the future, more expensive, specifically just with cost, phytosanitary pressures, and then of course this priority, particularly in Europe, for greener products and a lower carbon footprint. To solve the packaging problem, as I said, it's very difficult, but it can be doable, or it is possible. The problem is, like I said, it's risky maybe for one exporter, so it really has to be, the risk of it failing dramatically, you have to be confined, or you have to reduce those risks with some exploratory research, I think. I think the main problem, or the main thing, is also just to optimize or to constrain the design space is an immutable a container, and then the boundary conditions for the pallet base itself. And then from there it becomes a lot easier and there are far less sort of options. I illustrated in this example, we sort of optimize for cooling and space usage in the container. But going forward, if you would probably need to add other factors into your design. Specifically, manufacturing cost, very important. So, what kind of board would you need in your carton? Would your carton assembly machines be able to handle this design? All these other factors. How does it protect the fruit? Would the market accept it? And then general compatibility of that carton with the whole supply chain on trucks, etc. And yeah, I think I'll land it there. Thank you very much for listening.